Welcome back. This is part C of the concept video for section 15.6 triple integrals. So please refer to my section video for some of the problems that are done in this exercise, which is number 13. Number 13, you can refer to section video for that one. Number 13, and there are some more. Number 19, number 20, all these are done in section videos for this section. Please refer to the videos for section 15.6 for the above problems. Let's try this example here. Example number 3. Evaluate triple integral over E. Square root of x square plus z square equal square root of x square plus z square dv, where E is a region bounded by the paraboloid y equal to x square plus z square and the plane y equal to 4. So the solid region is given by the paraboloid and the plane y equal to 4. For the first step, we will call the given integral, triple integral as I, as we normally do. Triple integral over E, square root of x square plus z square dv. So what is E? E is a domain. E is the solid region bounded by the paraboloid y equal to x square plus z square and the plane y equal to 4. So it's a good idea to sketch roughly the paraboloid, the solid region E. So let's sketch the solid region. It need not have to be pretty, but just to give an idea so we can find out the limits in the exact way. So we are doing a rough sketch of this. That is x, y, and z. Y equal to x square plus y square, y equal to x square plus z square is a paraboloid directed towards the y-axis, right? So y equal to x square plus z square is a paraboloid. So the exponent of y is 1, so it is directed towards the positive z-axis. Positive y-axis. Positive y-axis. Then y equal to 4 is a vertical plane. Is a vertical plane passing through y equal to 4 and parallel to, and it is parallel to xz plane. The y equal to constant is always a vertical plane parallel to xz plane, the coordinate plane, xz plane. So we have a cylinder that is directed towards the y-axis. So if I roughly graph that, x squared plus z squared. So it's going to be a paraboloid. So if you look at if you look at the paraboloid, it is directed towards the y-axis because y is isolated, and it's a circular paraboloid. The mouth of the paraboloid, it's opening upward, opening to the side towards the y-axis, and it is intercepted by the plane y equal to 4. So it is intercepted by the plane y equal to 4. So this is a solid. So now we are going to integrate this triple integral. So we need the projection of this part y equal to 4 and y equal to x square plus z square, wherever they meet, the projection of it is on the xz plane. So what is the projection? What is the domain? Domain of the solid on the xz plane. So which is obtained by solving the two equations. One is the paraboloid y equal to x square plus z square. The other one is y equal to 4. If you set them equal, you get x square plus z square equal to 4. And because it's a projection, the domain is going to be x square plus, it's a disk whose equation is x square plus z square less than or equal to 4. So the domain D on the xz plane is all those xz such that x square plus z square is less than or equal to 4, which is the boundary is a circle with center at the origin and radius equal to 2. But we are talking of a disk, which the inside of the circle is also included. So the domain is this, and you have y running from x square plus z square to y equal to 4. So keep in mind this domain that we see here in this picture is actually on the xz plane. So imagine the disk, which is the projection of uh, this, the projection of this yellow part onto the xz plane, so which will look like this. So step 3, we are going to integrate now the triple integral over E can be divided into two parts, double integral over the domain, and then this is for the first two. Then for the third part, it is y equal to x square plus z square to y equal to 4. This domain is x square plus z square less than or equal to 4. So instead of splitting them into three parts, x, y, z, suppose you are going to do this. Of course, inside the integrand is going to remain the same, square root of x square plus z square dv. If you are going to keep this in rectangular form, the way you would do, x is running from negative 2 to 2, then you would say z running from, if you look at this part of the disk, you will say z running from negative square root of 4 minus x square to positive square root of 4 minus x square. Then you would do integration with respect to y, which is x square plus z square to, which is the paraboloid to the plane y equal to 4. You have to do all of this, which is kind of tedious if you keep the variables this way, dy, dz, dx in Cartesian form. Instead, what we are going to do, we have a handy polar coordinates. We are going to combine these two integrals. It is only over a disk, x square plus z square less than or equal to 4. So for that part, um, we can use actually the polar coordinates. So we can divide this integral as double integral over the polar domain. The polar domain is what? Polar domain is the d converted to polar, which is r comma theta. R runs from 0 to 2. The radius of the circle is 2. And then theta runs from 0 to 2 pi. So this domain over here in parametric form is converted to polar like this. That is what we are going to do for the first two. Then we will keep the other one integral over y as is. So it is integral over the polar domain. So it is integral, we can write 0 to 2 pi for theta. Then we can write this as r varying from 0 to 2, radius of the circle, radius of the disk. And you're going to integrate with respect to y. So x and z are constants. It's y times x square root of x square plus z square. Between the limits x square plus z square to 4, then dz dx is, in terms of polar, it's r dr d theta, because it's only dA on xz plane. In polar, it becomes r dr d theta. So we get I equal to integral theta varying from 0 to 2 pi, r varying from 0 to 2. And if you substitute here, you will be substituting only for y. That becomes 4 minus of x square plus z square in parentheses. So it becomes 4 minus x square times square root of x square plus z square. Then you have r dr d theta. Here, because we are considering x square plus z square in the xz plane in polar form, so we get x square plus z square equal to r square. So x square plus z square will become r square. So that using that, we will get 0 to 2 pi and 0 to r, 4 minus r square, because you can write this as negative of x square plus z square. That will be r square here. Then outside you have square root of r square, which will be r. Then in addition, we have this r dr d theta. So we can separate the variables here, integral 0 to 2 pi d theta, then integral 0 to 2, 4 r square, if you distribute, and minus r to the power 4 dr. So this will be 2 pi. This will be 4r cube over 3 minus r to the power 5 over 5 between 0 and 2. So it will be 2 pi times 8 times 4, 32 over 3 minus 32 over 5. That 32 can be taken out. So it will be 2 times 32 will be 2 times 32. That will be a 64. That will be a 64. 2 pi, 64 pi outside. Then you have 1 over 3 minus 1 over 5. That is 64 pi. That will be 2 over 15, which will be 128 pi over 15. So the value of the triple integral is 128 pi over 15. Right? So this was problem number, this is example 3. Then we will see how, what are the applications of triple integrals. Similar to the way double integrals were used to find the area of the region, using the formula double integral over d, 1 dA, we used this to find out the area of the domain. Because actually double integral represents of the volume, but if the height of the surface was taken as 1, then the volume becomes the area. So area of the domain, we used double integral to find out the area of the domain. Same way, we will use triple integrals to find the volume of the solid um, using the specific case f of xyz equal to 1. The formula for volume of the solid E is triple integral over E 1 dV equal to volume of the solid, that is volume of the solid E. Here A of D stands for area of the domain D. So there are problems based on this idea to find the volume of the solid. Even this one, find the volume of the solid. Problem number 19, 20, all these are done in the section videos. Please check the videos for this section to refer to the rest of the problems. Hope this video helps.